Good afternoon, everyone. Good afternoon. Thank you for joining us and welcome to this exciting webinar regarding control prototyping and power hardware in the loop for microgrid assessment. My name is Nelly Ratimoro. I'm in charge of the French market for OPAL-RT Europe, and I will be hosting this webinar today. So let me introduce our first special French guest to you. Yahya Bouzid. Yahya Bouzid is OPAL-RT Europe Technical Manager. He has an extensive experience of more than 10 years in the real-time simulation area. Moreover, he is permanently involved in providing the best adapted solution to our customers. Our three following guests are coming from CA and Grenoble ENP. They all are OPAL-RT's partners since years and involved in many microgrid and smart grids projects with OPAL-RT platform. Dr. Van Nguyen, researcher at the Grenoble ENP in the Grenoble Electrical Engineering Laboratory, G2 Lab. He has been working with the OPAL-RT platform in the field of his research regarding interoperability, advanced SCADA services, and holistic methods for cyber-physical energy systems. Professor Chuan Tran Kok, Professor, international expert at the CEA and scientific manager for smart grids at the CEA and INES, the National Institute for Solar Energy. He has been involved with OPAL-RT simulators in complex and various projects, including power grids and renewable energy, now for more than 15 years. And Dr. Raphaël Kerr, Associate Professor at Grenoble ENP at NC3, École nationale supérieure de l'énergie, l'eau et l'environnement, in the Grenoble Electrical Engineering Laboratory, G2 Lab. He also shares a strong and long 15 years experience with OPAL-RT platform in working on it for power electronic project and smart grid project. This is the webinar outline. So, first, Yahya Bouzid will begin the webinar with an overview of usual challenges in developing microgrids and how OPAL-RT real-time simulators can help you in addressing them. Then, Chuan Tran Kok and Van Nguyen will present SCADA services and power hardware in the loop technique for microgrid control validation. And finally, Raphaël Kerr will conclude the webinar with a presentation covering microgrid distributed control validation in the hardware in the loop environment. As you can see at the end of the webinar, we will have a few minutes for question and answer, depending on the time. So please feel free to send us your questions in the question box during the session and let us know to whom address the question. Very important, let us know to whom address the question. So it's now time to start. Let's begin with Yahya Bouzid.
Good morning, everyone, and thank you for attending this webinar about microgrids. Today, I will be discussing about the challenges that we can meet when trying to develop microgrids, and as well the benefits that can be brought by real-time solutions such as the ones provided by OPAL-RT. So the outline here, three big topics. So a couple of minutes about OPAL-RT technologies, about the company. Then we will speak about the challenges that we can face when trying to develop such systems, and we'll finish with the benefits that can be brought by real-time simulation. Well, OPAL-RT Technologies is currently the world leader in the development of real-time digital simulators, which are based on PC and FPGA technologies. They are used to design, validate, and optimize complex control systems. And they can, the systems that we develop, they scale up from compact simulators, as the ones we can see in the bottom right-hand corner, to large integrated test benches, which offer extra services such as mapping and harnessing and specific electronic conditioning. Obviously, not only do we manufacture hardware, but as well software that goes with it, which is used to design the models that we want to study. And in this case, we are speaking about microgrid models. So it's the power system part, but as well, whatever power electronics and control that goes with it. So what we do here is provide systems which allow to simulate both control and physical models. And at some point, we would like to connect these simulations to real physical devices under test. The fashion in which we do this will define whether it's a controller hardware in the loop or a rapid control prototyping approach. So this will be seen later. But basically, the idea is that we have something that is simulated, something that is real, and we want them to talk together. And depending on how we connect them together, we will be able to somehow ease the design or optimize the as well the configuration, validate complex systems, including controls, and maintain these systems even if they are already on the field. So why would we do such things? So what are the features or what are the use cases that we can find when using such real-time simulators? Well, different cases here. So if we just speak about the energy world and the power systems world, including the microgrids, there are three main topics. So the control system testing, system level studies, and protections. If we start from the one in the middle, the system level studies, so what we would like to do, or the challenge that could be brought by such complex systems, is that we need to analyze them in a very detailed way. We need to check what happens if there are faulty cases, what happens with cybersecurity, what happens with renewables integration, and generally speaking about how to deal with fast power electronic devices. We have to deal as well with the development of the control systems. So we need to debug all these complex algorithms and the smart things that we try to define here. We need to test the controllers and try to do this as fast as possible, because as you all know, projects are time limited, budget limited, so the faster the better. And in the end as well, protection, that's as well a trendy topic, where we need to test IEDs, so the intelligent electronic devices which are on the field. We need to check if they operate together. So we need to check if different vendors do manufacture systems that can work together. And generally speaking, we want to analyze protection schemes. So OPAL-RT, we have 7 offices all around the world, 280 employees, and more than 100 customers. So yeah, we try to cover the whole world and try to offer service as close as possible to our customers. Our customers include power systems customers, power electronics, as well aerospace, automotive, and other transportation sectors, and in both industrial and academic fashion. So we do work as well, I mean, with industries and as well with universities and research labs. Well, that was about OPAL-RT. Let's talk now about the challenges that we have to face when we are trying to develop microgrids. So there are different kinds of challenges. I would like to present or to introduce 3 big topics. So the technical challenges, economical, and regulatory. So technically speaking, when we are trying to define or to design a microgrid and the controls that go with it, we'll need to take care about different sets of operations. So the on-grid or off-grid operation, we might want to study what happens if we need to black start. Do we have grid forming capabilities in the microgrid? We need to balance the power, obviously. We need to define protection schemes. We need to have power electronics which are properly controlled. We are integrating renewables, and we have to take care as well of about interoperability of devices. Economically speaking, there are challenges as well. So mainly related to costs in terms of design or maintenance, and as well we need to find a business model to make the Mac. If it doesn't work economically wise, then there's no way it works technically. And the last but not least, regulations. So currently there are a lot of discussions about legal frameworks to sell and to purchase electricity, especially when it comes to microgrids. What are the policies to interconnect them with distribution grids, and as well relationship with utilities, and obviously competition, which as well can happen between microgrids or between microgrid operators and generally speaking distribution operators. So in the end, what we want to do here is not only deal with the electrical part of a microgrid, but as well with all these smart devices which are supposed to be controlling and monitoring the system. So we have many IEDs, obviously, that need to be connected to the microgrid to measure every single point of interest in the microgrid and control it properly. We have protections and obviously monitoring rooms to make all these things work smoothly. We need to ensure that they are properly controlled, that the power flow is as expected, that we can work in both on-grid and off-grid, then we can deliver a certain amount of quality in the service. So we have, we need to have stable voltage and frequency, for example. And all these things have to be studied at some point, analyzed, before we can build and implement the microgrid physically. We have the challenge around the distributed and intermittent energy resources. So as you know, if we are intermittent PV or wind turbines, well, the sun does not shine all the time, neither does the wind blow all the time. So the energy production here is not the same all the time along the day or along the year. So we need to take care as well in terms of controls about this intermittent energy and make sure that it's redirected in the right way to ensure the power balance at any moment. I mentioned rapidly the interoperability issues that we might face, especially when we have multiple IEDs on the field, which are speaking over different protocols, which come from different vendors, which of course are supposed to comply on standards. But as you know, implementation can slightly differ from standard. So testing the interoperability of IEDs is a challenge, and it needs to be addressed as well at the same level as all other challenges, which can be electrical or control based. Now the question is, well, why don't we just build it and test on the field? Let's do it and let's see how it works. And if we need to adjust something, well, we will figure out what to do. Well, the issue here is that we have an effect here that you might know. That is the cost of, let's say, repairing something when we detect that the issue very, very late. Actually, if a defect is introduced at the design stage, a very early stage of a project, well, the cost to repair it, to fix it, grows exponentially. So the later we detect it, the more expensive the correction will be. And it really grows in a crazy way. So imagine that we have some kind of blackout, things that happened, that happened from time to time, and there were some huge ones, especially in the US 15 years ago. Well, we are talking about weeks to restore the power, about billions of dollars to cope with the impacts. So these are things that we don't want to see very often, if possible. And a principle that is very important to know is that when we try to define here in a very, let's say, simple way, the different steps of a project, well, the design, implementation, validation, commissioning, maintenance, actually, we usually start detecting issues when we start validating the system, when we start testing. So this is the traditional way. So we design, then we implement, and once we have the product or something that looks like a product, we start testing. And this is where we start finding issues. This is not super cool because if we remember the previous slide, if we detect issues very late, well, the cost to repair them can grow very, very fast. So here, what we want to avoid is detecting issues very late, but it's what happens many times still today. Now, why don't we just create a prototype in the lab before we go real and see if it works? Well, first thing is that it's hard to perform full-scale tests because in the end, it would be a real system. So it's as if we deployed it on the field. And if we try to downscale it, well, we can question the representativeness of it. It's time consuming as well to have prototypes, can be very expensive, can be unsafe. So in the end, in some cases, prototypes are not a super good idea, even though they can help to do some tests, but we cannot rely on them to validate a complete product or a complete set of products, especially when they are super complex. So why is it hard to have full-scale prototypes or to test on the field? Well, in the case of grids, electrical grids, the question is, okay, how long shall I wait to capture a fault and see if my controls or my protections react properly? What happens if this interrupts service? So what if I'm impacting customers here? So that's a big issue. So if I'm on the field, there are some tests or some systems I cannot test in real conditions right away. It can be time consuming as well, because if we talk about the control part, so the algorithmic part, as you may know, we have more and more code, more and more software that is controlling all these complex systems. And just for your information, if you take just a car, like a high-end car of today, it's 100 million lines of code. So imagine if you are deploying hundreds of control systems on the field, and that you need to make sure that every single system is working properly. This could take, I mean, forever to test. It can be unsafe as well to work on real prototypes without being sure of what's going to happen. I think the pictures are telling what I mean here. We don't need to go further. So these are things we don't want to see either. So if I try to sum up things here in terms of challenges, on-field tests, which are hard to conduct, huge validation effort. Some cases are unsafe to test with real systems. We need to develop as fast as possible, and we need to take care of how much it costs. So in the end, what we want to do anyway is to validate these microgrids and the controls and the protections fully, efficiently, rapidly, economically, and safely. So these are a lot of requirements. We have a lot of constraints. And this is why we are introducing the concept of real-time simulation. And I will try to explain or to give you some clues about the benefits that can be brought by such simulation systems. So we are talking about modeling. So we are representing in a software way some complex systems that we want to assess. And in this case, it's testing controls and protections in a microgrid. So it could take ages to detect a fault in real life and to assess the behavior. So what we want to do here is to replace that physical microgrid by a software model that can be very close to reality. And we might want as well to connect this software model with some real devices that are under test, such as protections or controls. And here we can make thousands of runs, and we can trigger whatever case we want very safely. So in the end, this modeling approach helps facilitates the development of these systems. We need less prototypes. We can test very complex or unsafe cases in a safe way, and replace whatever hardware is not really physically available for the tests. So in the end, what we want to do here is, in a few words, just in a nutshell, replace real systems by real-time simulation. So we are creating some kind of digital twins or some kind of virtual representation of the system. And what is nice is that this thing is completely flexible, reconfigurable. You can do super crazy stuff, and it still works. Thanks to this approach, the thing is that we can start testing somehow the behavior very, very early in the project. So remember the traditional way where we start discovering possible issues at the end of the process? Well, thanks to the simulation, we can start discovering things very early at the design stage before we even create any physical prototype or any physical system that is doing on the microgrid. Everything is virtual, so we can test whatever case we want, and even before we have any physical things sitting on the lab or wherever we want, we still have these software-based prototypes that can help us to see how things are going and if the strategy we are using to control and protect are working properly. So two approaches that we can mention to this, to illustrate what we can do with real-time simulation. We have the model in the loop, which basically means that we want to simulate, so we want to use software models of the complete system. So the microgrid, whatever it is connected to, such as the distribution grid, and whatever control systems or protection systems that we want. And we can observe the behavior of the system through different test scenarios. We can have different levels of observation, so we can zoom a lot and see down to the power electronics what's happening, or zoom out and see more in a power flow way the behavior of the system. We have the hardware in the loop approach, where we want to test some physical devices. So here on the left of the picture, For example, see how protections or controls interoperate together when they are as well connected to a microgrid, and see if the whole setup is working properly. So here we are getting a little bit closer to reality because we start having some physical devices connected here. There are other ways that we can think about, such as the Power HIL in the loop, where we have part of the microgrid that is real, part of it that is simulated. So we can go very, very far away in the testing and get closer and closer to the, let's say, final setup that will help us assess that the microgrid will work properly. So as a conclusion, as you all know, there is a boom today in the development of microgrids. Their development is super challenging, technically, economically, and regulatory-wise. If we just focus on the technical part, we do have tools that facilitate the design, the development, and the optimization of these microgrids. Thank you very much for your attention.
Thank you very much, Yahya. Amazing presentation. So now we move to the next presentation. Trent Hancock and Van Oa Nguyen.